Hi everyone, welcome to chapter 18. After our long excursion through thermodynamics and a very brief excursion into kinetic theory of gases, which is a subset of stat mech, we're finally now moving over to kinetics. So that's very exciting. Here's your reading for this week, and with that, let's go ahead and begin. So here's what we're going to be talking about today. I have a few notes about the transition from thermodynamics to kinetics. Then we'll see what a reaction rate is, because that is the most important quantity probably in kinetics, and how the entire subject of kinetics is described by a so-called rate law expression, and how that relates to rate order of the different components of the reaction. We'll see how the rate law arises from the reaction mechanism, and we'll take a look at a type of reaction called a first-order reaction, and then see how to compute the half-life for a first-order reaction. So the main difference between thermodynamics and kinetics is that thermodynamics is in a sense timeless. Time is not considered when dealing with thermodynamic problems. Kinetics, however, does concern itself with time. Thermodynamics asks, okay, well, if you waited an infinite amount of time, then what would happen? Would the reaction move forward or backwards? What would be the final concentrations of the reactants? What would be the heat released? Given enough time, like an infinite amount of time, for the system to reach perfect equilibrium. In kinetics, we are not actually at equilibrium, but somewhat close to equilibrium. And so as the system moves in the direction of equilibrium, we can ask, how are the concentrations changing with time? Like, that's a very common question that we're going to be answering with kinetics. And since life itself does not exist at equilibrium, but most of the time very close to equilibrium, kinetics is very well suited to dealing with the biochemistry of life. So most of the time when we're encountering biochemistry in a medical context or in a molecular biology context, we'll be dealing with kinetic quantities. Now, I'd like to return to what I said earlier, that kinetics concerns itself with systems that are close to but not exactly at equilibrium. So therefore, what sorts of systems would lie outside the realm of kinetics? Well, explosions, for instance, or shock waves are things that would not be describable using kinetics. They're just too far away from equilibrium. We will consider those very briefly near the end of next chapter. And it's worth noting that though life does exist very close to equilibrium most of the time, that's not necessarily always the case. For instance, if you have not seen the video about the pistol shrimp, I highly recommend that you pause this video right now and go look it up on YouTube. It's very interesting. There's an example of how a biological creature is using a situation very far away from equilibrium in order to obtain food. So anyway, quick note before we move on. For the rest of the next two chapters, when we are asking about the concentration of some substance A, we'll put square brackets around it, okay? And by the way, this is going to be in molarity. We're not going to be dealing with molality really at all, I suspect, for the rest of the semester. So when you see the square brackets around A or around some other substance, then you know that's the molarity of that substance. To start, I'd like you to consider the following reaction. Substance A goes to substance B, and that's it. There's one product and one reactant. An example of a reaction that could occur that would be like this might be the unfolding of a protein. So if I have a protein here, and I got an alpha helix, and I've got a nice beta sheet right over there, that one might be unfolding like so. It's denaturing, perhaps, maybe due to high temperature or something like that. Now this is going to take time to occur, and so I'm going to make a plot here. Down here is time, And then over here is going to be the concentration of A in black, and then I'm going to indicate the concentration of B in red. So A, since we're starting out with a large amount of A, it's going to have a higher concentration at the beginning and then slowly decrease over time. And then as time gets very large, then it will approach zero asymptotically like that. Okay? B, on the other hand, probably starts at zero concentration, though not necessarily. There might be some unfolded protein just existing inherently in the system. In that case, the dot would be higher up starting out, but B is going to come up like this and then also approach some asymptotic limit. All right. Now this point right here, we're going to call concentration of A 0. So the concentration of A at time 0, because that's time 0 right there. And we can choose that time 0 arbitrarily. We can make it whatever we want. Now the thing I want to point out to you here is that near the beginning of the reaction, say right there at a fairly early time, notice that the slope of this curve is steeply down. But then out here at a later time, the slope of this curve is much more shallow. So if I were to write change in the concentration of A with respect to time, we have this derivative here. That's going to be a very negative number right over there. But then down here, that derivative is going to be only slightly negative. And it's negative again because the slope is pointing downwards as time goes forward. So this is how reactions proceed. They tend to go fast near the beginning, and then they tend to go slow near the end. This is called the rate of the reaction, this derivative, dA with respect to t, negative. And we can write out the change of concentration with A as a function of time, and I'm going to make it negative because it's going to be a negative number, and it is going to be the exact same as the rate of increase of the concentration of B. And this is going to equal some function, that's what this F represents, some function of the concentration of A and perhaps also of the concentration of B. Okay? Now, whatever this function is, I'm going to write down what it is for this situation very soon, but this function will be called the rate law expression. And for this example, the rate law expression is going to look like this. The change in concentration of B with respect to time, which of course equals the negative change in concentration with respect to time because it's disappearing, because it's a reactant. This is going to equal some constant K times the concentration of A. All right? And this K right here is called the rate constant. And we'll look at rate constants a little bit more. I also want to put a little 1 up here because if that concentration is raised to the 1 power, then that means it's just that value, concentration. And this is called the rate order. And in this case it's 1, but it could be a different number. And so let's take a look at another example here for a different type of reaction where that will have a different rate law expression. We may have 4 nitrogen dioxide. It's reacting with an oxygen, and it's going to form dinitrogen pentaoxide. And it so happens that the rate law for this is the change in the concentration of N2O5 with respect to time which we could just call the rate, is equal to a different rate constant, NO2 to the second power times the concentration of O2 to the 1th power. And so as you can see, there are different orders above the concentrations of each of these. We would say that this reaction is second order in NO2 and it's first order in O2. Now, final note on this particular reaction, let's compare it to the equilibrium constant expression. And remember, that's big K. The equilibrium constant expression would have the products on top, N2O5. We can express it as a concentration. It's going to be to the second power. And then we have the reactants on the bottom to the 4th power and O2 to the 1th power. Notice that the equilibrium constant expression and the rate law do not equal each other. They're substantially different from one another. The equilibrium constant expression is easy to obtain if you just know these stoichiometric coefficients. The same is not true for the rate law. We have to actually know the intermediate reaction mechanisms to predict what the rate law would be. And we'll get to that in just a moment.